Hello, class. So, week one, first topic. There'll be two topics for this week. This is the first one. Fluid properties and pressure, okay? So what are we going to be talking about? Basic concepts for fluid mechanics, units, variables, and very simple formulas, okay? We'll take it easy first week here. I think you have access, there should be a PDF of these notes too that you'll have access to as well. These notes here, okay? So, what are we going to be learning today? A couple of different things. Fluids versus gases. We're going to define pressure. We're going to talk about different units, different equation setups, force and mass relationships. I think you guys probably know this. Newton's second law. Force equals mass times acceleration. We're going to define density, specific weight, specific gravity, and bulk modulus. If you're wondering if you guys have the book, it's chapter 1 in the book. Okay. So, fluid mechanics, the study of the behavior of fluids. So, this is what generally it is. So, there's fluid statics, so fluids not in motion, coffee in the cup, or fluids that are in motion, fluid dynamics. That would be like a river flowing, okay? So why isn't this called liquid mechanics instead of fluid mechanics? So a fluid can either be a liquid or a gas. So we'll find out. And it might be a little bit counterintuitive, but gases behave very much like fluids. And we'll get into that. So matter either exists as a fluid, a solid, or something called plasma. So we're not looking at solids, we're going to be looking at fluids. We're not looking at plasma. So plasma, what is a plasma? It's a significant number of molecules have been ionized. So, either a solid or a fluid or a plasma have different molecules within them. So ionization, electrically charged particles subjected to electromagnetic forces. So they're created by adding energy to a gas so that some of the electrons leave the atoms. If you're interested, there's a link, as you continue on your studies, if you choose to, you'll learn a little bit more about that. But we'll not be looking at any kind of plasma, okay? So in fluid mechanics, we're concerned on the macroscopic, not the microscopic level. So big picture, basically not seeing the forest for the trees, okay? So the volume that we deal with is small compared to the dimensions of the system of interest. So if you think about like a big water distribution network, the volume is small compared to the system overall. But for fluids, it's large compared to the distance between the molecules of the substance. So how the distance between these molecules. So spacing of molecules for fluids is in the range of 10 to the negative 6 meters for gases, 10 to the negative 7 for liquids. So the number of molecules in even a tiny volume of fluid is huge. So treat fluids as a continuum, meaning that the matter of the body is continuously distributed and fills the entire region of the space it's occupied. So it's not discontinuous, right? Okay. So matter, solid versus gas versus liquid. They basically just differ in how the molecules are spaced. The range of molecular motion and the levels of intermolecular cohesive forces, okay? So again, what's the difference? Spacing, how they move, and the level of how cohesive they are, okay, between the two molecules. You can imagine molecules in a gas aren't quite as cohesive as molecules in a solid. So solids have extremely small spacing, low range of motion, and high cohesive forces. That's what makes them solid, okay? Gases have relatively large spacing, high range of motion, so they move around all over the place, and low cohesive forces. And liquids are just somewhere in between, a solid and a gas. So previously those were just words. This is sort of a figure that shows it a little bit more. What do we have here? Solid, you can see those lines, those are the interconnective forces that keep the molecules close. They're pretty connected. So lots of times what happens generally, this isn't for all matter, but generally if you add heat, it'll transform a solid to a liquid, and then a liquid to a gas, generally. So you can think about this as in water. You know, solid water is ice. You add a little bit of heat, it becomes liquid water. You add more heat, and it becomes a gas, it becomes steam, okay? It's a classic example. It's not true for all bits of matter, but generally it is true for what we'll be dealing with mostly. This is true. So fluids under stress. So what are stress? Different types of forces. We've got compression, tension, torsion, shear. You guys probably talked about this in your previous courses. Compression is when you're pushing on it, tension is when you're pulling on it, torsion is when you're twisting it, and shear is when you're trying to tear it in opposite directions. So fluids have elastic properties under direct compression and tension. So what did we talk about before? Elastic behavior. Basically, you know, it goes back to, it's just like similar to an elastic band. You stretch it, you compress it, and it eventually goes, if you let off the force, it goes back to its original configuration. Shear stress, even a small amount, will result in a continuous and permanent distortion of the fluid, and it gives the ability of the fluid to change shape or flow. So, shear stress. Ketchup. Okay, so you know, ketchup, if it's just in the bottle, it's not moving, it's not doing anything. You have to give it a shear stress in order to get it to flow. You know, even if you have to stick a knife in the bottle, okay? For practical engineering application, fluids are assumed to be unable to support tensile forces. So, yes, in engineering practice, I mean, can you imagine trying to put, I don't know, coffee under tension? It doesn't really work, okay? So fluids, how they behave under stress, okay? So a solid resists gravity forces, tensile forces, shear forces, and initially maintains its original shape. As the force increases and elastic deformation takes place, once the elastic limit is exceeded, it comes under permanent deformation. So if you remember from our mechanics course, mechanics of materials, we had the plastic portion and then the elastic portion of the stress strain curves, okay? In a liquid such as water, it spreads quickly and it forms a puddle, aka permanent deformation. It flows, okay? You know, you try to take a cube of water and you put it on the counter, it's gonna turn into a puddle. So honey, it spreads, it's different from water, it's different than a solid. It spreads but more slowly. It's because the viscosity is greater than the water and therefore has a greater shear strength. Viscosity will be the second portion of this lecture. We'll talk a little bit more about that. So, you know, this is solid water and honey, but some materials fall in between these classifications, somewhere between a solid and liquid. So this could be slurries, I guess you could call it a Slurpee, tar, silly putty, toothpaste. They will act as a solid under initial application of shear stress, but once the critical value is exceeded, they will tend to act like a fluid and start to flow. Okay, we'll get all into this, don't worry. Gases. So what does a gas do? A gas will also spread and form a puddle if on Earth, if the gas is denser than air. So, you know, you can imagine fog, you know, sometimes it you know, sits on the ground, or yeah, there's a carbon monoxide poisoning. It tends to be a little bit heavier than air, and it doesn't float or disperse. So here's some rules. Generally, liquids will take the shape of the container and go to a uniform level. What can you think? A glass of water, a cup of coffee. They just, you know, we pour the coffee into the glass, the mug, and it takes the shape. Gas under pressure will expand to fill a container. So you can take like a gas and you have to put it under pressure in order for it to go into a vessel, basically. Liquids are slightly compressible depending on what liquid you're talking about, and gases are very compressible. So you can imagine helium. They compress the helium to fit those containers, right? So you got a lot of gas. If you try to put a bunch of water in that same helium container, you probably can't put as much. Okay. So let's talk about some common quantities. Most of these you're familiar with already from your previous classes. So you've got length. This is usually meters or millimeters in engineering terms. Sometimes in imperial you will learn that I can't take and I despise imperial so much, but that would be a foot and an inch. You probably have heard before. There's time, so those are second, hours, and that's basically in standard units as well as imperial. We've got something called mass, which is the quantity of a substance. Kilograms in metric. It's something called a slug in imperial. There's force or weight, so it's the push or pull of an object in standard units, SI units. It's a Newton, and in imperial it's a pound. Pressure, which we'll get into, it's just a force times area, so it's a Newton per meter squared commonly. That's a Pascal, or it's a pounds per foot squared, PSF, or PSI, pounds per square inch. You'll see both those. We've got energy. It's the force times distance, so force newtons times distance, meter, or pound per foot. We've got power, which is the big P, so pressure is little p, power is big P. Power, you got energy divided by time, so generally called watts or Newton meters per second, joules per second. We'll get all into this. Or pound foot per second in imperial. Volume is just length cubed, so meter cubed, foot cubed, inches cubed, millimeters cubed. Area is length squared, meters squared, millimeters squared, foot squared, inches squared. Volume flow rate, so this is what we'll be concerned with a lot in fluids, is the flow rate, the volume flow rate, large capital Q. So it's the volume of over time. Meters squared per second, liters per second, foot squared per second, so cubic feet per second, gallons per second, gallons per minute. You'll see all sorts of different things. There's something called the weight flow rate, which is newtons per second, pounds per second. Mass flow rate, capital M. So mass over time, we've got kilograms per second, kilograms per hour, kilograms per minute, slugs per second. Okay. Specific weight is gamma. You'll see this lots. We'll be talking a lot about this. Okay. So it's weight or force over volume. So newtons per cubic meter, kilograms per meter squared, times second squared, or pounds per foot squared. And density, rho, which it's the mass per volume, so kilograms per meter squared, or slugs per cubic foot. We'll get into it. Okay. So let's start with mass. It's for fluids. It's the measure of the fluid's resistance to change in motion. So remember, force equals mass times acceleration. So it's a measure of the resistance to that change in motion, that acceleration. It also is a measure of the quantity of a fluid. So lowercase m, it's in kilograms. Because it's force equals mass times acceleration, you know, the units come out in newtons second squared per meter. And something called a slug. Again, we'll go into that a little bit more later on, like what is a slug, not just the green thing you see in the garden. And they're also, again, for use of units, it's pounds second squared per foot, but nobody generally calls it that. Okay, so weight, it's the amount of the body of fluid weighs. So depending on if it's in a container or how much it is. So force with which the fluid is attracted to by the center of gravity. So like anything, okay, it's the pull towards the earth. So you're going to weigh, or the fluid's going to weigh something different at the top of Mount Everest, or sea level, or on the moon, or whatnot. But again, generally we, for this course, we live in a world of sea level gravity. Okay. So what are these equations? So the weight, W, is equal to the force, which is equal to the mass times acceleration, which is the mass times gravity. So the weight is just mass times gravity. What are the units in metric? It's a newton. I think we're all familiar with newtons now. You've got newtons and kilonewtons generally is sort of where we live in. And gravity, for the most part, is 9.1 meters per second squared, or 9.1 newtons per kilogram. And in SI units, hopefully we won't encounter them too much. This is pounds, and gravity is 32.2 feet per second squared. Those are like, so G is a constant, right? It's a constant on Earth at sea level. I mean, you start getting into different scenarios, but it's like a matter of decimal places, which we won't have to, generally not too concerned with in engineering, depending on what it is. If you're developing a telescope, it's very different than if you're developing a site for like a subdivision, okay? So common quantities. So what do we have? Density, rho. It's the mass per unit volume of a substance. You probably have seen this before. So what's the equation? Rho is equal to the mass divided by the volume. So the units come out kilograms per meter cubed. Okay. So the density, mass per unit volume. Remember when we looked at the water and the honey? So the density of the water is quite different than the density of the honey. Okay. Other thing that we'll be dealing with a lot is specific weight, gamma. It's the Greek letter, again, lots of Greek letters, okay? So it's the amount of weight per unit volume, which is equal to rho, what we talked about in the last slide, times gravity. Comes out in newtons per cubic meter. So, you'll note that density and specific weight are related. So the specific weight, that gamma that we talked about, is rho times g, which is the weight per unit volume, newtons per meter cubed. And the weight is equal to the mass times the gravity. So gamma, the specific weight, is equal to the weight divided by the volume, which is mg, mass times gravity divided by the volume. And density, rho, is the mass per unit volume, which is a kilogram per cubic meter. So rho is mass times volume. So if you relate them both, we've got gamma equals mg over volume, which is also equal to rho g. So there you go. The specific weight, gamma, is equal to the density times gravity. So what do we have? Mass, lowercase m, it's in kilograms, or Newton times second squared per meter. We've got acceleration due to gravity, g, lowercase g, 9.81 meters per second. We've got the weight, which is the force of gravity. It's in newtons, lowercase w. We've got density, rho, kilograms per meter cubed, and we've got specific weight, gamma, newtons per meter squared, and we've got volume, meters cubed. Sorry, specific weight, newtons per cubic meter, okay? Generally. So units. Write out the units when solving every variable and quantity. Do it every single time. Because it makes it easy to convert before and after during solving. When you're looking at it, does it make sense? Like, sometimes you'll look at some numbers. Again, it goes with practice and guidance, if it makes sense, okay? And if you carry the units throughout the whole calculation, this is the same for all your courses. If the units come out as expected, newtons per cubic meter per se, then it's a good chance the answer is right. If the units come out wrong, then most likely your answer is wrong, okay? And slugs. This is where we get to talk about lovely old slugs, okay? So what is a slug? A slug is a unit of mass in U.S. customary system, so imperial system. It's in the pound, which you're probably used to, is a unit of force. So the pound is therefore a unit of weight, since weight is defined by the force of gravity. Force equals mass times acceleration on the object. So if the mass in U.S. customary units is 1 slug, it's equal to 1 pound times second squared per foot. Weight is equal to mass times gravity. So we got this 1 pound second squared per foot times 32.2 feet per second squared. So the pound force is 32.2 pound force, which is what that figure is showing. You got 1 pound weight and one slug. Very different, okay? So you'll see, it's quite common to call both mass and weight in pounds. It's another reason to dislike imperial units. And you'll see this on a lot of, where do you see this? On specification sheets for things. You'll see pound M, so that's pound mass, and you'll see pound F, which is pound force. So often if mass, 1 pound mass, 1 lbm, is equal to the 32.2 pounds foot per second square force. It's not the same. A modified and cumbersome form of Newton's laws to overcome this. So what's the point of this? Generally, we're going to be using metric, if I could help it. But if you do see a slug, it is the mass, okay? So, enough about slugs. Pressure. What is pressure when it comes to fluids? So it's anything. Force, pressure, force exerted on a unit area of a substance. So in this course, we're using lowercase p for pressure, and it's the force divided by the area. And in this case, it's the weight times the area. So fluid you can see that one diagram that we've got there. Let's see now, there it is. If you've got any point within a fluid, all the pressure acts uniformly. So from the top, from the bottom, from the side, it's all uniform. Okay. Fluids this is like in the ocean or a river or whatnot. If the fluid is confined by solid boundaries, so it's in a container, in a pool, in a coffee cup, whatever, the pressure acts perpendicular to the boundaries. So you can see there we've got a furnace duct. So in your house, if you look up, you can see where the ducts are coming out. They're square, they're acting all perpendicular. We've got a pipe or tube. We'll be dealing a lot with pipes and tubes. Heat exchanger for a pipe inside another pipe, okay, which happens. So basically you got a pipe, usually water is used. You'll see this a lot in industrial plants. So you have water on the outside tube, something on the inside tube that needs to be cooled down, transfers the heat. You got a reservoir. What's a reservoir? Can be a dam, can be a, you buy a jug of water. Swimming pool. I bet you everybody this summer probably wish they had a swimming pool. We've got a dam there. That's an earth dam. We'll be going through that, I think, in this course, if not for your soils class. And fluid-powered cylinders. So, you can see fluid-powered cylinder. What do we have? Liquid in a solid boundary. There's a force that's acted on it. Try to squish it down, and it causes pressure on the side. Okay. So the important things to know here, again, pressure, force over area, weight over area. The fluid pressure acts uniformly in all directions, and in confined space, the pressure acts perpendicular to the boundaries, okay? Don't worry. Once we go into the application of it, you'll see it. So what's the common quantities of pressure? Newtons per meter squared, or kPa, or PA. kPa is kilonewtons per meter squared, or you'll see PSF, pounds per foot squared, or PSI, pounds per square inch. Okay. There is a conversion there, so PSI, pounds per square inch, is 144 pounds per square foot. Okay. Rules. So at any point, the pressure is the same in all directions. We talked about that already. And pressure increases linear with depth for a liquid. Okay. Uniform liquid. Okay. So what is the gamma for water? It's telling you there. So the pressure at the surface of the water is 0. There's no pressure acting on it. Atmospheric pressure, but we'll get into that later on. It's generally 0. If you go down half a meter within the water column, this is probably fresh water, not salt water, at a certain temperature. We'll get into it again. It's 4.905 kPa, and at 1 meter it's 9.81 kPa, and at 2 it's 19.61 kPa. So we'll do this one in our study group on Wednesday, but give it a try. If not, I'm sure you can look up the specific weight, gamma for water, but we'll do it too so that we can work through it. Okay. So static pressure, that's another rule. Static pressure is independent of the shape or vessel or volume of water above the point. So you can see here that that's dyed water in a very strange shape vessel. You can see that all the water has gone to the same elevation. So at point A, at point B, at point C, at point D, they're all the same pressure, despite the shape of where it's at, right? So A has got like a bigger area than say C, but the pressure is the same. This is called Pascal's paradox. So any pressure on the surface of a fluid other than atmosphere is directly added to the fluid. So what do we have here? We have a container that we're looking at. It happens to be 3.5 meters deep. It's filled with water, and you probably did that, right? We've got, so the gamma for water is, well, this is in Newton meters cubed. 9,810 newtons per meter cubed. You're timesing it by the height, which is 3.1, and you're adding that imposed pressure, 1,500 newtons per meter squared, on top of it. So follow that through, and you've got 35,835 newtons per meter squared, or pascals. Just divide that by 1,000 and you get kilopascals. 35.8 kilopascals in this case. Okay. In what world would you do this? Yes, lots of industrial applications. Okay. Specific gravity. Specific gravity is important concept. It's a convenient way to either express the specific weight or the density of the fluid. Okay, it's related to both of them. It's expressed in terms of a fluid's relationship with the specific weight or density of a common fluid. Generally, this is pure water at 4 degrees C. So pure water, not salt water, pure water at 4 degrees. And 4 degrees C happens to be the densest it'll ever be. So water is denser at 4 degrees C than it is at 10 degrees C. So it's a way to express any kind of fluids. Yeah, like I said, specific weight or density with relation to water. And it's handy because it's independent of the unit of the system that you're using. So it's the ratio. It's the ratio of its density or weight compared to pure water. what's that mean? For example, the specific gravity of seawater in this case is 1.030. I have some comments on this that I'll talk about later. So if the specific gravity of this particular seawater is 1.030, the specific weight of the seawater is, so that gamma that we talked about, is the specific gravity times the specific gravity of water, which we already did, right? Which was 9.81 kilonewtons per meter cubed, or 9,810 newtons per meter cubed. So you just multiply the specific gravity at 1.030 times the specific weight, and you get 10.10 kilonewtons per meter cubed. So you'll see lots of published values for different fluids for the specific weight, the gravity, the density of different fluids, and you'll also see the specific gravity. So you'll see those three things published all over the place in tables. For this course, we'll either give it to you, or you find it in the back of the book, find it in tables. You can look it up on the internet. The problem with the internet, I'm sure you guys already know, is that sometimes things are published wrong. Usually what I learned is to look at 3 different sources and then figure it out. But for the purposes of this course, we'll either give it to you or find it in the back of the book. Okay? It'll be specified, we'll tell you. So common quantities, specific gravity, again. So it's the relationship between the specific weight of common fluid and generally water in this course. So specific gravity is the ratio between the specific weight of the fluid divided by the specific weight of water at 4 degrees, or the specific or the rho, the density of the fluid over the density of water. It's dimensionless. So you can apply it. It's kind of good because you can use it for metric or imperial. So gravity, negative 9.81 meters per second is equal to negative 32.2 feet per second. Why negative? It's just a sign convention, right? Down is negative in this course. Density of water, rho, density of water at 4 degrees C is 1,000 kilograms per meter cubed, or 1.94 slugs per feet cubed. Hence another reason why I like metric so much more. 1,000 is a lot easier to deal with than 1.94, but it is what it is. We get stuck with these things. Specific weight of water, gamma of water at 4 degrees C is 9,810 newtons per meter cubed, 9.81 kilonewtons per meter cubed, or 62.4 pounds per foot cubed. When I was doing this course, much like you guys, one of the guys I was going to school with, he worked for a water company, and he was lugging around those big jugs of water all the time. We used to do that conversion. So if you've got the book, see now, let me get it. Here's the book, okay? So other factors are found in the appendices, so let's flippy-flip and find it. So Appendix A in the book, there it is. It's properties of water. So this explains how, we'll get into this too, but just a little preview. How the specific weight, the density, changes with the temperature of water. That's why they always use this 4 degrees C. It's got it in both metric and imperial. There's other Appendix B, okay? There's properties of common liquid, so it's got specific gravity, specific weight, density, dynamic viscosity, and kinematic viscosity. We'll get into that later on, of a bunch of different liquids in both metric and imperial. Okay. And then there's typical properties of petroleum, which again, we do live in a world where there's still quite a bit of dependency on the oil sands, so you might have to deal with that when you start working. Okay. Compressibility, bulk modulus. Okay, so this is the compressibility of a liquid. So it refers to the change in volume of a substance related to the change in pressure. So remember we said with certain liquids, they're slightly they slightly change their volume depending on the pressure, and it's called, this is measured in the bulk modulus elasticity. So E, it's the same, so it's the same nomenclature that we used in mechanics of materials. Liquids are very slightly compressible, so values of E, this bulk modulus of elasticity, are generally very high, and generally we consider liquids to be incompressible. So I have to use that a lot with what I do. I have to assume that the water is incompressible. Gases are compressible, but the term bulk modulus is not typically applied to gases, and we refer to gas law when discussing compressibility of gases. We'll get into it, don't worry. But I guess the main point here is just to think of liquids as generally incompressible and gases as compressible. Okay. So bulk modulus, the compressibility of a liquid, it's change in volume related to the change in pressure. So E, big E, capital E, is equal to the negative change in pressure. Again, that's just a sign convention, divided by the change in volume of that liquid divided by its original volume. And so it's, you can see by the equation, you've got change in pressure, which would be force times area, or pascals, divided by dimensionless unit, so it's going to come out in units of pressure. Okay. So common quantities of bulk modulus. What do we have here? We've got alcohol, 896 MPa, so that's megapascals, that's 10 to the 6 newtons per meter squared, however you want to look at it. Benzene, machine oil, you can see, so benzene is 1062, so you have to put 1062 megapascals of pressure onto a unit, volume unit of benzene in order to make it change any kind of volume. Machine oil, water, glycerin, mercury, you can see that this happens to be at 20 degrees C. So this is the bulk modulus for different liquids at atmospheric pressure, so in the air, and at 20 degrees C. We're going to find out that liquids and gases behave very, depending on the pressure. That's this, and the temperature in which it's at. Okay. So problem 1, a tank of water is open to the atmosphere, indicated by the little triangle. Yes, there's lots of little triangles. That's how I have to do it too. A little triangle and a couple of lines. That's the surface of water. At 4 degrees C, find the volume, density, mass, weight, and pressure on surface it is sitting on, so on the bottom of the tank. So what's the plan here? Normally in a classroom setting we would just do this problem, but it's easy. You guys, I'm going to set you free, give it a try, and then on Wednesday we'll go through it, okay? We'll go through some hand calculations and you'll see it. Okay, great. The other problem that we can work on too to demonstrate these are all problems to help demonstrate the concepts that we just went through. So what do we got here? Problem 2, fluid is oil. You've got the specific gravity of 0.92. So oil is, find the volume, density, mass, weight, and pressure on the surface of the cylinder it's sitting on. So the bottom of the cylinder, again, the diameter is 0.5 meter. We've got 2 meters depth of this oil, okay? So we'll do that again. Like I said, I encourage you to go ahead and try it because, again, gives you guys some practice on this. Problem 3 that we'll go through, and again, you guys should go through it too. An unknown material has a mass of 342 grams. Now remember, it's grams, not kilograms that we talked about. And a volume of 1.8 times 10 to the negative 4 cubic meters. Find its density, its specific gravity, its weight, and specific weight. So that's density is that rho, specific gravity is that dimensionless quality. The weight should come out in kilograms or grams in this case, depending, just be clear. And the specific weight, that's at gamma. Another one that we'll go through is got this motor oil with a specific gravity of 0.887. What volume would have a weight of 12 newtons? Oh geez, 12 newtons of motor oil. Not super fun to be carrying around. So, next one. For mercury with a gamma of 132,800 newtons per cubic meter, what is the volume of 92.0 grams sample of mercury, and what is the specific gravity of mercury? So remember, the specific gravity is just its relationship to water, pure water at 4 degrees C. Problem 6. What pressure is the bucket exerting on the surface it's sitting on in PSI? Imperial units. So PSI is pounds per square inch. With no information is given about the fluid, assume it is water at 4 degrees C. And we've got, so I think that one was what, 32.2 whatever per whatever. It's in the notes there or the back of the book. So we've got a cylinder, the bucket, dear Liza, 1.5 feet high and a diameter of 0.7 feet squared. 7. So this liquid is oil, specific gravity of 0.9. What is the pressure at P1 and P2? So they basically, so they've got a pressurized vessel. In this case, it's a bike pump that they use to pressurize it. Sure, why not? To 50 kPa. Okay, so you're looking for the top of the oil and the bottom of the oil. 2.6 meter depth. Problem 8. Calculate the force on the shaded area of the water pressure. So, hello, look at that. Fun! So we've got this L-shaped container. Water at 4 degrees C. Overall height is 2.9. We've got some basic dimensions of the container. 0.3 for the width of the little leg. 0.8 meters overall, and the little leg is 1.9 meters. down. Okay. Problem 9. Before any force is applied to the volume of the sample of machine oil is 1,000 liters. So, or 1 liter. 1 liter is 0.001 of a meter cubed, I think. Force F is applied, causing the pressure to rise about 4,000 psi, or 27,579 kPa. So why 4,000? Well, there's a lot of changing of units in this one, so I guess that's the trick in this one. Unfortunately for us, most of the pressure measuring devices in real life, if they're old, happen to be in this PSI. Hopefully life will change soon. Calculate the new volume and magnitude of the force F. So remember newtons or pound forces. Perform your calcs in both metric and imperial. Oh, this will be fun. Okay. So if it says C mot, book figure 1.4. Flippity flip. Figure 1.4 6E. Found 1.0. Oh, 6th edition table 4. Oh, okay. So it's that same. You guys saw this in the notes here. Okay, so 9 problems. First lesson. We are doing a second video too, so we're going to be talking about the viscosity of fluids, but we'll go, like I said, I encourage you to give you these 9 problems a try, but we'll go through them on Wednesday at 10:30. It'll be a live class. We'll do it through Zoom, but like I said, my plan is to record them too, so that you guys can have access to it all later on. But first lesson, first class, here we go.